Hi, everyone. So welcome to the last section of Math 142 as covered by me. We're going to be talking about some models for population growth, which are sort of bedrock models of differential equations that are used in biology and chemistry, physics, and engineering. To begin with, I'd like to talk a little bit about the justification for the natural growth model that we talked about in the last section. So the natural growth model had the following form. dp dt is equal to kp, where k was the constant of proportionality or constant of growth, and p of t is a function that tells you the population at time t. What could justify this model? How do we get to just say that the change in a population is proportional to whatever's happening in that population at a time? So the big justification here comes originally from observations about bacteria. So bacteria, in their natural state with unconstrained resources, tend to multiply by exactly dividing in two. Cells generally act like this. In the presence of unlimited resources, cells will continually divide, and then the new cells will divide, and then the new cells will divide, and so on. And so you could get behavior like if you started with 6 cells, and then you let them sit and grow and split, then the next time you look at them, you might have 12 cells. And the next time you look at them, there are going to be 24 cells. And when all of those split into 2, you'll have 48. And the idea is, as long as you're consistent about the time between each fission, so say this is an hour, and this was an hour, and this was an hour, then essentially what you're saying is you've got a model where if you drew some dots to represent the population, so 6, 12, 24, 48, you can see already that this looks like an exponential growth curve, because what's happening is the slopes are approximately doubling as you go up the curve. So the observation to make here is that you can see that there's a relationship between the change in population in the next part and what that population was. And that's what justifies thinking, well, maybe I can find a constant of proportionality that tells me what the relationship is between the current population. I multiply by some number, 1 in this case, and that tells me how much I'm supposed to increase in the next chunk of time. Now we can symbolically solve this differential equation to get all the solutions to every possible natural growth problem. If we write down dp dt is equal to kp, and we use the method of separation, we're going to get dp over p is equal to k dt, and that's going to say that the natural log of the absolute value of the population is equal to kt plus c. Populations we typically assume are positive. I don't know how to have negative foxes, for example. And so we could rewrite this as p is equal to e to the kt plus c, but e to the c is just some constant a, and it's going to turn out to be the case that I can tell you what every piece of this is. The k is the growth constant. This constant a, remember, which is really just the secret of this e to the c here, because this was equal to e to the kt times e to the c. And since c was arbitrary, e to the c is arbitrary. A is actually equal to p of 0, because p of 0 is equal to a. And so that means a is the initial population. The next thing that we want to do with models once we have them is start to add on to them in ways that describe new situations. So the next thing we're going to talk about is a model that shows up in a lot of areas, including economics, called logistic growth. The motivation for this model is the fact that populations grow exponentially when there's no constraints on those populations. That is, when resources are unlimited and there's no constraints on space, for example, or competition. When those things start to influence the way that a population grows, we get a type of behavior called carrying capacity behavior, which is to say, at some point, the population is going to start running out of easily available food, or they're going to start competing with each other for things like nesting places or things to eat. A phenomenon that's been observed in nature is that populations tend to asymptotically approach a limit called a carrying capacity. And you shouldn't think of it as a limit. It's not a hard limit. Populations can go over. But the way that populations grow looks like this. They start and they grow to the carrying capacity, and then they asymptotically approach that. It's also possible that they could start and then grow so quickly they go over the carrying capacity. But then there's too many organisms to be sustained by whatever the environment is. And so what we would expect to have happen here is that they die off and then come back down to whatever the maximum long-term capacity of the environment actually is. So the challenge is to try to get this kind of behavior to have some sort of limit or asymptotic condition that the population will approach into the model that we're writing down. So this model is clearly not sufficient because all anything in this model is ever going to do is grow. There's no way for growth to stop here because the bigger the population gets, the bigger the change in population gets. So we're going to take this and we're going to add a term to it that's supposed to control the behavior of the population in the case where the population gets close to M. And the easiest way to do that algebraically, there's a lot of things you could write down here. The easiest algebraic thing to write down is the term 1 minus P over M. Equivalently, you could write down M minus P, and then you'll have an M factored into the K later on. But this term, if we think about it, should give us the asymptotic behavior we're looking for. After all, what is the slope of these functions as they get closer and closer to the carrying capacity? Well, it's 0. As the growth slows down, we should expect the slope to flatten out to nothing. What does this term do as P gets close to M? Well, the closer P gets to M, the closer this number gets to 1, and 1 minus 1 goes to 0. So as P goes to M, this term goes to 0. As P goes to M, this term is controlled by M, so you have a constant M times something that's headed to 0, which means you get this flattening. What happens if the population is over the carrying capacity? Well, in that case, what's going to happen is this number will be bigger than 1. If P is bigger than M, P over M is bigger than 1, and 1 minus something bigger than 1 is negative, which means in that case, what will happen is this slope will be negative, which will mean we're getting growth down to the asymptote in the long term. So this term seems like it adds everything that we want to our equation. And indeed, this is called the logistic growth equation. Now we can solve this similarly to the way that we solved the natural growth equation, but it's going to be more involved because there's more variables in here. So we'll do that on the next slide. Using the technique that we learned in 9.3, we can rewrite this with separation as dp over p times 1 minus p over m is equal to k times p. And in that case, on the left-hand side, we're going to have to use partial fractions because we have this rational function over here. So you can factor 1 over m out of the bottom and then put the reciprocal in place, which will give you m over p times m minus p. And then what the partial fraction step will let you do is write this as 1 over p plus 1 over m minus p. So there's a lot of algebraic ways to set this whole computation up, but this way gets you the ones on top, which is the easiest possible way to proceed. So let's pull that back over onto this side. So now what we have is the integral of 1 over p plus 1 over m minus p times dp, and that's equal to the integral of k dt. On integration, we're going to get the natural log of p. Because the variable in the second term is negative, this actually turns into minus the natural log of m minus p. And on the right-hand side, we get kt plus c. So one sort of standard convention here is to multiply through by -1, and so that you end up with the natural log of m minus p minus the natural log of p is equal to minus kt plus c. And then when you do that, you end up with m minus p over p is equal to e to the minus kt times e to the c. So we can think of that as being a, right? So the e to the c here is just some constant a. And if we work through the math for m minus p over p is equal to a e to the minus kt, you can do this by multiplying by p, subtracting it over, factoring, and then dividing. What you're going to end up with is p is equal to m over 1 minus a e to the minus kt. And this is the logistic growth function. It turns out to be the case that when you evaluate this thing with the initial population condition, you can furthermore say that the constant a is not the initial population like it is in the natural growth model. It's equal to the carrying capacity minus the initial population divided by the initial population. So what does that actually measure? It's the proportion of the carrying capacity that the model has already taken up, right? So m minus p tells you how much carrying capacity is left as a raw number, and then dividing by the initial population tells you something about the percentage of available capacity left. What we've sort of been through here are the natural growth model, which is dp dt is equal to k times p, which has solution p is equal to a e to the kt, where a is equal to the initial population, and the logistic growth equation dp dt is equal to k times p times 1 minus p over m. Remember, that's the thing that gets us the carrying capacity, and that has solution p of t is equal to m over 1 minus a e to the minus kt, where now a is equal to m minus p naught over p naught. I prefer not to memorize these solutions. I prefer to work them out as I go, as necessary, but you're more than welcome to just write down the solutions unless I explicitly ask you to derive the solution in a particular case. I was mixing two different derivations of the logistic growth solution together, and I want to reiterate that, as is now correct in the notes, that there's a plus sign in the solution to the logistic growth equation in the denominator of the final function. So it's supposed to read 1 plus a e to the minus kt. Okay. So what other models can we have? Well, there's lots of ways of modifying these. So there are some pretty interesting ones where you have, say, a predation rate or a death rate. So you might have a model that looks like... So I'm going to write a model down, and let's see if we can interpret what exactly that model is saying. So if we have change in population over time is proportional to the current population times 1 minus p over m, that is, it grows logistically. There's an initial population, we have early growth that's exponential, that's what the p does, and then the 1 minus p over m makes it tail off as we get close to the carrying capacity. But suppose it's a fishery, and every once in a while you're harvesting a fish. Well, that means every unit of time you have a certain number of things that are, a constant number of things that are being pulled out. So a harvest. I pull out 100 fish a day or 100 fish a year out of a particular population. How does that affect the model? That will be explored in the homework questions. Another model you might have would be one where there's a minimum population, where once you drop below some number m, the population tends to collapse because the animals can't reproduce anymore, for example. That can be modeled with change in population over time is equal to kp for the exponential growth at the beginning, 1 minus p over m to account for the carrying capacity, and then one term that tends to drag you once you get below the minimum population. So this term sort of acts in the opposite way that this one does. This drives you up towards a carrying capacity. When p gets close to m, that makes this thing get close to 0. What happens here? Well, now the p is on the bottom. So if p is smaller than m, then m over p is a big number, and that makes this negative. And if this is negative, it makes all of the rest of it negative. So this is a way of forcing the growth of the population to be negative once you go below a certain line. So we can also think about modeling in situations where we have more constraints or conditions. And the art of modeling a lot of times is in choosing exactly which term should be here, and then testing these models against real data to see if you've captured the behavior that you're interested in. But building out differential equations like this is basically what a scientist does. Scientists measure observations in the wild, and then they get back into their labs and they model those situations frequently with differential equations that look like this. A more sophisticated approach to populations is to look at them as interacting with each other. And that means that we have multiple equations like this that have terms that include each other. So that is a very sophisticated idea with a very sophisticated set of techniques. It's called dynamical systems or systems of differential equations. You will see that in much higher level classes than this one. But this is the gateway towards the core of modern scientific understanding of the world. So with that said, here's some word problems. Everyone's favorite, so go do it. And I will talk to you guys later.